So of course the other question they love asking is induction. So let's just go over a couple of ideas with induction. Inequality ones, whilst of course you can see them in extension 1, they are more common in extension 2. So here's our pattern here. Test n equals 1. So left hand side we get 1, right hand side we get 1, and yes, 1 is less than or equal to 1, it's equal to 1. So it satisfies the condition. Now, remember, do not set it out the way I'm about to do it. This is just to save some time so we can get through some more examples. Our assumption would end up being 1 plus, etc., etc., etc. We want to prove k plus 1, so that's what we want to prove. Okay, well, it's a series type, so I'll rewrite it with the kth term and the k plus 1th term, substituting the assumption less than or equal to. Now, I'm not going to touch that 2 because what we want to prove does go 2 minus something. So it would be silly to incorporate the 2 into the fraction, only then to later on having to pull it out again. So I'm just going to play with the algebraic fraction, but got to be careful here because I'm going to leave the negative out the front as well, because what we're trying to prove is 2 minus something. So when I do that, my second fraction is negative k on top, not plus k, because negative times negative would give me the positive there. So be careful with that. Now, let's expand the top out. We're trying to find, what was it again? It was 2 minus 1 on k plus 1. So that's what we're trying to head to. So ideally, looking at my denominator, I would like to have k outside of k plus 1 to cancel on the top. And then that would just leave me with 1 on the k plus 1 that I want. Of course, I don't have that. I've got k squared plus k plus 1. But that's the beauty of an inequality. So what I'm saying is I'd like on top the k squared plus k. Don't have that. I've got also the minus. I'm going to pull out that minus 1. That's the bit that I don't want. The fraction that I've got left with is the fraction that I want. But because I'm dealing with an inequality, if I look at this fraction, we know k is positive. We assumed it was a positive integer. K plus 1 squared, of course, is positive. So I'm subtracting something positive. So if I'm subtracting something, this line, second last line, has to be less than the line below. Because the second last line is the line below, but minus something positive. So it must be smaller. Right? Now, that's now got me to where I want, and it cancels, and we get to what we want to prove with. So that's the beauty, I suppose, of inequations, is that unlike equations, we don't have to do the same thing to both sides. As long as we preserve the inequality, the less than or the greater than, we don't wreck that one up. Now, different in extension 2 is sometimes we have these interesting ones where we have more than one term that we're playing with. So this one here is we've got this sequence. The first term is going to be the square root of 2. Every term after that is going to be the square root of 2 plus the term previous to it. And we're going to show that every single term in this pattern is always less than 2. So it's not a series as such. We're not saying what's the sum of the whole thing. It's just each individual term is going to be less than 2. So if I test it for n equals 1, well, they told me the first term is the square root of 2, and the square root of 2, of course, is less than 2. So that's fine. I will therefore assume that term k is less than 2. I want to now prove that term k plus 1 is less than 2. Now that's where the formula they gave me, remember that formula, an plus 1, I don't have to prove that. They have given me that as a fact. What I'm proving is an is less than 2. And that's the link that I will use to get the assumption in there. So they told me that k plus 1th term would be equal to the square root of 2 plus the kth term. So that's a fact. I don't have to prove. That has to be less than the square root of 2 plus 2. Because we said term k was less than 2. That was our assumption. But 2 plus 2 is equal to 4. The square root of 4 is 2. So term k plus 1 must be less than 2. Bingo, we have our answer. So I think the mistake people sometimes make with this is they feel like they have to prove the general term that's been given to you. If they've given it to you, it's a fact, so you can use it. Then you get these interesting ones where actually we've got two patterns going on here and they interact with each other. So the X pattern, we've been given the first terms of each pattern, but to get the second one in the X pattern is I get the first one in the X and the first one in the Y divided by 2. To get the next number in the Y pattern is I double the product of the ones before and divide it by, and so on. So we want to prove that X to the n times Y to the n will always equal 10. So first term, x1, y1, well they told me x1 was 5, y1 was 2, 5 2s are 10, so okay, it works for the first one. We now are going to assume that xk, yk is 10. We want to prove xk plus 1, yk plus 1 is also 10. Let's substitute in the pattern that they told us was a fact. So xk plus 1 will be xk plus yk over 2, and yk plus 1 will be 2xk yk over xk plus yk, and actually it just drops out quite nicely. We can see the numerator and the denominator will cancel, the 2's cancel, it just leaves me with xk yk, which we've assumed is 10. So yeah, okay, that works. It'll always equal 10. The Fibonacci, I love the Fibonacci sequence. So the classic Fibonacci, which starts with the first two numbers being 1, and then every term after that, we just add the two previous terms. And we're going to prove that every single term in this pattern is less than 1 plus root 5 on 2. Significance of that is the golden ratio, to the power of n. Okay, so a lovely little relationship with the Fibonacci pattern. Now, here's the interesting thing. When you look at the formula we're going to use, because remember, we're going to use this formula to substitute in my assumption. But there's two things I'm going to have to substitute in, an and an minus 1. So because I'm going to make two assumptions for this one, I need to prove the first two terms are true, not just the first one. So I've got to prove for 1 and 2, which they've told me is 1 in both cases. But so the first term's 1, and 1 plus root 5 on 2 is 1.62. So yes, the first term works. The second term, also 1, but 1 plus root 5 on 2 squared is about 2.62 and so on. So yes, the second term works as well. So yep, it works for both. So I'm now going to assume both of these things that I have to substitute in are correct. So I'm going to assume both term k is less than 1 plus root 5 on 2 to the power of k, and term k, well I've gone k minus 1. I could have done k plus 1 and then prove k plus 2. I've decided to go k minus 1 and k and prove k plus 1. Doesn't really matter. Basically we just need 3 consecutive things there. So we're going to try and prove term k plus 1 is less than 1 plus root 5 on 2 to the power of k plus 1. So okay, there's the formula for the pattern of the Fibonacci sequence. Sub in my two assumptions. So 1 plus root 5 on 2 to the power of k plus 1 plus root 5 on 2 to the power of k minus 1. And we're trying to show that this is less than 1 plus root 5 on 2 to the power of k plus 1. Well, I'm going to actually factorise, but factorise a little bit differently. Normally we would take out the lowest power when we factorise, but I'm not going to do that. I'm going to take out the k plus 1 that I'm trying to prove. And then I'll just play with the other factor. Because if I can now show that that other factor is less than or equal to 1, then I've got it. Because power of negative 1, turn it upside down, 2 on 1 plus root 5, and then square it and turn it upside down, 4 on 1 plus root 5 squared. Well, let's make the common denominator 1 plus root 5 squared. So we now get 2 plus 2 root 5 plus 4, which is 6 plus 2 root 5. And you'll never guess what 1 plus root 5 all squared is. 6 plus 2 root 5, sure enough, it does expand out. So that's just 1. So now if we read down our solution, we've got that ak plus 1 is less than 1 plus root 5 on 2 to the power of k plus 1. Now, sheets So I'm trying to remember what I put in the handouts. I must have put in some induction questions in there. 10E in Patel.